Welcome to the presentation of our paper DeFIX, Detecting and Fixing Failure Scenarios with Reinforcement Learning in Imitation Learning-Based Autonomous Driving. This research was conducted by me, Resul Dagdanov, and Feyza Eksen with supervision of Professor Nazim Kemal at Istanbul Technical University AI and Data Science Research Center and e-tron Technologies Company. The main goal is to detect failure scenarios of imitation learning agent and fix infractions by training reinforcement learning agent on constructed mini scenarios. Firstly, let's take a look at the problem statement. We have chosen Carla challenge environment for our evaluations and trainings as it features realistic urban driving cases with adversarial scenarios such as pedestrians emerging from random locations, vehicles running in red lights, or getting stuck on the highway. Designing a perfect rule-based agent would necessitate a lot of hard coding to tackle these scenarios. An objective of this research is to come up with a new continual learning methodology that solves the shortcomings of a suboptimal policy by identifying failure locations of imitation learning agent and training different reinforcement learning agents on the infraction spots. Carla offers an autopilot vehicle that uses privileged labeled information from the simulation, such as exact positions of nearby vehicles, pedestrians, and traffic lights with correct signs and orientations. We have observed that even an autopilot vehicle could not finish the predefined challenge environment routes without violating any traffic rules, as it is very sensitive to predefined rules. So directly imitating an autopilot will result in a lack of performance of the trained policy. And imitation learning is a method of behavior cloning where a neural network model is trained in a supervised learning manner, particularly to mimic the input and output mapping of expert policy demonstrations. In our case, a rule-based autopilot agent. Our method called DeFIX has two general stages. In the first stage, an initial dataset is created by saving front camera observation, GPS location, vehicle orientation, and action command of an autopilot vehicle. An initial imitation learning model is trained with collected demonstrations. The main objective of this stage is to apply data aggregation or Dagger algorithm continually until the performance of an imitation learning agent gets closer to the performance of the demonstrator policy. In the next stage, Dagger cantilevered imitation learning agent parameters are freezed and tested on the simulator. Infraction and failure locations of evaluated model are extracted from the predefined routes. Episodic mini scenarios are created from infraction spots, and different reinforcement learning agents are trained on these mini scenarios. Then this newly trained RL agent is added to the library of RL agents to be used in the future evaluations. A policy classifier network is trained in a supervised manner where the ground truth labels are determined by the sign of their privileged reward function. At each step of evaluation and inference section of this stage, custom reward function is calculated and stored to train policy classifier. As it is known which scenario is triggered, we can group all similar scenarios with negative returned rewards to be the ground truth labels of the policy classifier model. We have two similar networks that are trained in a supervised learning manner. The first one is an imitation learning agents network which classifies a single Boolean braking action. We have observed that the brake action is a more dominant than throttle and steering actions. As the waypoints of the track are given in Carla challenge environment, for throttle and steering actions, we have used low-level PID controllers. Vehicle speed, orientation, location, and front camera data are obtained from sensors while sequential target locations are given priorly. Another supervised learning network is a policy classifier which has the same freeze ResNet backbone with the same observation space. However, these two networks are trained separately with different labels. The ground root labels of the policy classifier are trained agents including an imitation learning agent. We have used DQN method to train an RL agent. Fully freezed ResNet backbone features of front camera images represent the state space of reinforcement learning agents. The reason to fully freeze and use logits of ResNet backbone as an observation space is to extract useful features from camera images. High-level action commands to train DQN are shifting predefined route waypoints to left, right, or lane keeping or stopping. For low-level throttle and steering actions, the same PID controllers are used. Custom reward function is designed for determination of labels and trained RL agents. The sign of this reward function references whether to assign imitation learning agent for current scenario or switch to one of the trained RL policies. Positive return of this function represents correct action performance of an imitation learning agent without any traffic rule infraction, while negative return shows that an infraction is occurring and the switch to another policy should be held. In the experiment section of reinforcement learning training, blue framed figure on the right shows one of the training scenarios, while orange framed images refers to similar test scenarios for trained reinforcement learning agent. During the training, for generalization purposes, weather conditions are changed dynamically and the agent is initialized from random distances to the infraction spot. We have observed that this trained DQN agent was capable of solving all stock vehicle scenarios in this town. In the results section, the table on the left shows the effects of a data aggregation algorithm in the first stage of DeFIX method. After each loop of stage 1, imitation learning models route completion, driving, and infraction scores are increased until the route completion performance gets closer to that of an autopilot performance. Bar chart on the right shows the total number of infractions against methods in the literature. We see a huge drop in number of blocked vehicles and agents getting stuck on infractions due to the power of generalized reinforcement learning agent. However, other infractions are not changed when using a DeFIX method because other scenarios require different RL agent to be trained on the specific failure scenario. By comparing our method against current Carla Challenge benchmark competitors, we outperformed with 15% better route completion score and close or better driving score. We can see that our method performed better than privileged autopilot policy without using any privileged labeled information from the simulation. Scores show that even by training one generalized reinforcement learning agent on one infraction scenario of imitation learning agent, increased driving score and route completion scores significantly. In conclusion, we have demonstrated that imitation learning policy is limited with the performance of the demonstrator policy. To further increase the performance while achieving safe autonomous driving, we proposed and tested DeFIX method. The future of this work will focus on extensive tests on different maps and scenarios of the Carla simulator. The confrontation of new challenges and failures will expand the library of RL agents and will broaden the effectiveness of the policy classifier. We believe that our DeFIX methodology could spark reliable, robust, and safe autonomous driving technologies. Thanks for listening.